at section 1.5. 1.5 is graphical transformations. And I know you went over graphical transformations in Algebra 2, because I taught it last year. So, it's coming back. We are going to add one graphical transformation that we did not talk about in Algebra 2. It's horizontal stretch or shrink. We only talked about vertical stretches and shrinks last year. We're also going to look at some different types of... Oh, actually, one graphical, that's 1.6. I forgot to change the title of that. I lie. This is parametric and inverses. Oh, inverses. This is a good time. So graphical will be tomorrow. Parametrically means that we're going to look at a function, and we're going to look at them, but they're going to be defined by a parameter. Usually we use t. Usually it's a source of time. Not always, but usually. And x and y are both use the variable t. All right, so it's a different way to graph something. So let's look at this. So it says consider all sets x, y defined by the equations. So if you notice, x equals something with a t in it, and y equals something with a t in it. Yes? Yeah. So this is a system of equations defined parametrically. We have a parameter. The parameter is t. Okay? So to find the points determined by this. So what we're going to do is we're going to make a t table, but instead of having 2 columns, it's going to have 3 columns. Because we need t, we need x, and we need y. Because how do we graph functions? What are the 2 variables we need to graph? X and y. So we got to kind of kill off the t to figure out what this thing is going to look like. Okay? So let's try it. Find the points determined by... So there it is. So you're going to have a t column, an x column, and a y column. And they told us what t's to use. And so for the x column, I'm just going to replace the t up in your equation that you can't see. That's on your paper. In the x equation, so I'm going to replace that t with those values there and figure out what my x's are. So if I replace x with t with a -3, what do we get? -2. And if I replace it with a -2, -1. If I put -1 in there, 0. What are these going to go up by? +1, and you could tell that from the function. So it'd be 1, 2, 3, 4. Are we okay with the x column? Now we do the same thing in the y column. Except for now the equation is this. So -3 squared. And then 2 times the -3 is -6. So 9 minus 6 is 3. Put a -2 in there. 4 minus 4? 0. Put a -1 in there. I got -1. Then I got a 0. Then I got a 3. Then an 8. And then a 15. Is that correct? Yeah. Okay. And when they say find the points, we're going to now ignore the t column because we use t. So what they're saying is, a pen, different color. They're saying this is here's the point. Here's a point. Those are the points that we're going to plot. Because our plotting system is in x's and y's. So we just use the t value to get to what x and y are. Find an algebraic relationship. So when they ask you to find the algebraic relationship between x and y, what they want us to do is what we call eliminate the parameter. We want to kill off the parameter. We want to get the t gone. So to get rid of the t, you look at both of these and say, well, which one would be easier to solve for t? The top one, right? The thing without the square. So can I take this and make it look like t equal? Yeah. How? Okay, so we did that. And now we're going to take the y equation. But instead of a t, we know that t equals x minus 1. So you're going to substitute it in. right? We actually want to simplify this out. So what's this do? What's this look like, right? This first part. X squared? Good. Don't forget the middle term, because if you wrote this out, you'd have to FOIL it, right? And there's a middle term. Common mistake. Plus 2x minus 2. So you get x squared minus 1 is y. And the question is y a function of x? So that means, does y equal something with an x in it? Yes. So is it a function of x? Yes. Woohoo! And the last thing we want to do is actually graph it. But we have all these points here. We can graph it. No problem. Yeah. But it's fun. If you think of it as work and painful, then it will be work and painful. But if you think of it as this is kind of a fun thing to do, guess what? It won't be as painful. And it'll be more fun. It's all up here, guys. It's all up here. Now, am I gonna plot anything to do with the t?
No.
No, just the x and the y. So negative 2, 1, 2, 3, 4, 5, 6, 7, 8. Okay, so negative 2, 3. And then negative 1, 0. 0, negative 1. 1, 0. What shape is it making?
Parabola.
A parabola. Which we should expect because we have a square in there, yes? Okay. And I understand that I'm not going to be able to do the 4 and the 15, and I'm okay with that.
You got a cup ready, girl?
Oh my gosh, I still do.
I knew you would. Good morning, class.
Nectar of life. Thank you.
I was a waitress in a diner for 2 weeks, and I got fired. I was that bad. I couldn't remember when people would ask me for something on my way somewhere. I couldn't remember what they asked me. Like, I forgot. I'd put orders in my pocket and then go. Someone would distract me, and I'd forget to give them to the cook. So people would just wait and wait. Terrible. I'm a terrible waitress. It was so hard. It was way too hard for me.
All right. Good to know. I've never done that, and I think I'd be the exact same way as her. I'd be like, what? Well, you guys have asked me a question, and then 5 seconds later, I'm like, somebody talk to me? So, it happens. It happens. Okay. So, we're going to learn how to use our calculator in parametric mode. So, I need you to get out your calculator. Nikki, come here. Okay. Now the cool thing about parametric is what I'm gonna show you on this right here. So, got your calculator out? Maybe? Some of you do?
So what's schedule? When's first?
I have no
It's
idea.
like 8:40 or something.
Something like that. So, hit mode, please. Not funny. Hit mode. Normal is fine. I always have mine on float. It would really make me happy if your guys' was on float too instead of some weird decimal rounding thing. Radian degree doesn't matter. What we're looking at is we've always been in function mode. And today we're going to try a new one out. It's called par or parametric. Hit enter. So highlight it and hit enter. Okay. Now you ready to hit y equals? Crazy things. So hit y equals. I've obviously done this question before. So if you look, if you type in this equation, and I guess I should point this out too. This is our variable button, and normally when we hit it, it makes an x. But we've moved one mode over, so what's the next thing next to the x? It's a t. In parametric mode, this button is going to give you the t. This is your variable button. You need to hit this t, not this pre-programmed t somewhere else, okay? So we're going to go t squared plus 2t. Are you okay with the x? Now, and if you hit enter, did the equation light up? Did the equal bar light up? No. In order to graph something in parametric mode, you have to have an x equals and a y equals. You have to have both in order for it to work. And so parametric is t plus 1, the y. Then they lit up, right? Now, before you hit graph, let's go to our window for a minute. We have some new things in our window. We have a t. We have a t min, we have a t max, and we have a t step. Okay? We have to play with these. So in the example, they want us to look at t's from -3 to 3. So do you notice my t min is at -3 and my t max is at 3? Because they asked my t's to be from -3 to 3. Leave your t step as 0.1. I'm going to show you what the t step does here in a minute.
So we should change it to 0.1 if it's possible.
Yes, please. 0.1 should be fine. And the rest of my window is the exact same as a standard viewing window. -10 to 10, -10 to 10. Are we okay? So let's see what happens. Oh, except for my window wasn't -10 to 10. It was to 80. It should have been 10. There it is. Yay. Parametric lets us graph things that aren't functions. How cool is that? That's pretty cool. I'm not gonna lie. It's pretty neat. Because look, they switched the x's and the y's. X is now the thing with the square. Is that okay? So is y a function of x? No. And then we want to find, and I'm going to play with the calculator here in a second. They want us to now find the algebraic relationship between x and y. So then you have to look, which one's easier to solve for t? The y. So let's take this equation and solve it for t. How do we solve that for t? Subtract 1. And then we're going to plug that in to our x equation. So what we have is we're going to have x equals something with a y in it. And that tells me it's not y as a function of x. It's x as a function of y, which means it's really not a function. And if you simplified it out, you should get x equals y squared minus 1. Are we good there? So let's go back to your calculator for a second. Did you notice it kind of stopped at a weird spot right there? So if you go to your window and you change t min to -5 and t max to 5, you get more of the graph. So when we graphed it where they wanted us to graph it, it was starting at when t was -3. It didn't graph anything prior to that. Now here's what else I'd like you to try. So let's change our t step. Change your t step to 5.
Like regular 5?
Just a 5.
Whoa.
The t step says how often do you want to calculate something. So when I said t step is 0.1, that means every 0.1, it put a new point. So it's calculating for 0, 0.1, 0.2, 0.3, 0.4, 0.5, and it was plotting all those points. When I put in t step is 5, it calculated at -5, 0, and 5. It only calculated 3 points. And then it draws straight lines between them. So that's what happened. So if you get a funky looking graph, and you're parametric, I'm going to be like, what is your t-step? If your t-step is a big number like 5, and you get something that looks absolutely crazy insane, I'm going to be like, there it is. That's why. So, and if you change it back to something small like 0.1, oopsies, 0.1, it makes it smooth looking again. So that's what the t-step does. It's how often are you going to calculate a new point. Is that okay? We feel okay with the calculator part on that? I'm sorry. Couldn't. I'm not going to do that because we don't have a lot of time. Inverse relations. So, remember how I gave you guys the quiz and I totally should not have, I used the wrong addition and you guys were trying number 4? I'm going to teach you how to do number 4 now. So, an inverse relation, now remember a relation is a set of ordered pairs. We've talked about a relation a little bit, but we don't talk about it very often. So a relation is a set of ordered pairs. So they say if we have an inverse relation, if and only if, you guys remember that from geometry? IFF. So if we have an ordered pair, you see what happened? What happened to the A and the B? They switched. That's an inverse relation. Okay? So what happens to your x's and y's on inverses? We switch them. We flip them over. Okay? So here's a really big deal. And I get a lot of kids that go off to college and they're like, oh my gosh, I totally knew what this was. And my teacher didn't yell it and it was super crazy. So we know how to tell if something's a function. We draw the vertical line. Yes? Well, how can you tell if something has an inverse that's a function? The horizontal line test, huh? Ah! So, an inverse of a relation is a function if and only if each horizontal line intersects the graph at most one point. So think of a parabola. Let's think of a parabola. Is that a function? Yes. Is the inverse a function? The inverse is not a function because the horizontal graphed it and hit it twice. So we have a function, but the inverse will not be a function. Yeah? Yeah, see? Kind of cool. Okay.
Like a straight line.
A straight line would be, the inverse would also be a function, yes. A cubic, the inverse is a function. Yes? You switch x's and y's, so instead of being like this, it would be like this. It would fail. If you graph the inverse, you would fail the vertical line test. So it means the inverse is not a function. We'll do examples. So look at page 122 for me, please. So the question is, I want to know, do we have a function, and is the inverse a function for each of these, okay? So let's look at the first one. Is this a function?
Yeah.
Yes, what function is this? The reciprocal function, it's 1 over x. Good. I want you guys to recognize that. Would the inverse be a function? So think of horizontal lines. Yes. Is a function, inverse is a function. So let's look at this one. Is this a function?
No.
Would the inverse be a function? Yes. Is that a function?
No.
Would the inverse be a function? Is this a function? Would the inverse be a function? No. Good. Good. Not gonna happen.
I agree.
Here's a big deal. 1 to 1. Okay? So 1 to 1 tells me two things. It tells me I have a function and the inverse is a function. Okay? So it is a function, has an inverse. You're going to say this with me like 500 times. Is a function, has an inverse. Okay, if I'm loud, they should not only hear me down there. You understand what I'm saying? How many of you are in here? Like 24 of you? There's no way I should be louder than 24 people. Roy, I want to hear your beautiful voice when I say this. So clear the throat right now. Okay, ready? Is a function, has an inverse. Is a function, has an inverse. Much better, thank you. Okay. So, when you go to college, and your teacher is like, we have a 1-to-1 function. I want you to think of, is a function, has an inverse. Instead of writing 1-to-1, we actually will go like this. So, We don't have to. So 1 to 1. Has an inverse. Now the other cool thing, so if we switch our x's and y's, guess what else switch? Our domain and our range. So we're going to spend a lot of time finding the domain and the range of the original function. So then when we find the new function, the inverse function, we don't even have to think about it. The domain and the range just flip-flop. I don't even have to think. It just does. Okay? Okay. This does not mean 1 over f of x. This means the inverse of f. So this means inverse.
Like the one on the test.
Yeah, like the one I shouldn't have hedged you.
If you got it right.
I want you guys to think of 1 to 1 so much that when coach yells go 1 to 1, I want you to be like, is a function has an inverse, and then do what he asks. Listen, then when he says man on man, I want you to think 1 to 1, and I want you to think is a function has an inverse.
1 on 1, or unless he's like, 1 on 1 right here. Hold on. ISO. What you got, son? Post him up. Eat him. Rock.
Is he gangster?
Nah, it's ball talk.
Oh, okay.
Lingo.
Whatever that is. All right. So we need to find the inverse of this. So before I start working on the inverse, I want to find the domain and the range. So domain I can find algebraically. So for f of x, the domain is what can x be, or in this case, what can x not be? Negative 1. Negative 1 soft bracket. Negative 1, 2. Yep, union. Now for the range, what are we going to do? We're going to graph it. It's not 0. Can't wait to teach you guys the shortcut. It's not really a shortcut. It's a long cut. Oh my goodness. I can't graph it.
Change it.
How do I change it?
Mode.
Okay. Function.
That's right, we're smart. 1 on 1, baby.
Oopsies.
You go too fast. Now you go to...
It's right here on your paper. I'm not making it up.
Your calculator speed is just unrivaled.
I doubt that. Okay. What's it look like it's plateauing to? I heard it. 1. So if you just hit trace and go out like far. Oopsies, I didn't do my dim or my window right. Let's go 50. It looks like it's totally flat plateauing. At 1. So that's my range. Okay. So your range is negative infinity to 1, 1 to infinity. Okay. So, in order to find the inverse function, whenever I see an x, I'm going to put a y, and wherever I see an f of x or a y, I'm going to put an x. So I'm going to flip-flop stuff, okay? So, I need that for later. So, instead of f of x, I'm going to go x equals y over y plus 1. That's how you find inverses, okay? And now what we need to do is we need to get y all by itself. So right now my biggest problem is I have a y in the denominator. Do not cross off those y's. There's a plus in the denominator. They do not cancel. If you cancel that, I have like 0 sympathies for you because I've emphasized that so many times it's not even funny. So, don't do it. Resist the urge. It does not work. I promise you this. So, what I'm going to do is I'm going to multiply both sides by the denominator. And on the left, I'm actually going to distribute the x through. And then the y, those cancel. On the right side. Now I'm trying to solve for y, right? So I need to get anything that has a y with it all on one side and everything else on the other. So I have an xy over here and I have just a y over here. So we have an x kind of throwing me off right there. So what do I need to do? Nope, don't divide. Because then we're back with y on the bottom. Doesn't this no good? Minus the xy. Move it over. So you have x equals y minus xy. Don't divide yet. What do both of these have in it? So when we're going to factor it out. So we're left with 1 minus x. Now we can do what you guys have been wanting to do. Now we can divide by y minus x. Or 1 minus x, sorry. That's our inverse function. And I would like us to, instead of y equals, how you write inverse is you say the inverse of f of x is equal to x over 1 minus x. Now, there's no shortcut way. You have to work it out. There's no set rule that, oh, look, the numbers are the same. They're just do it. Okay? So this is proper notation. And what happens to our domain and range? They just flip. So for this, the domain would be whatever my range was. And my range is whatever my domain was. I don't even have to think about it. It just is. Now, sometimes it's hard to do this algebraically. So we're going to do it graphically. Don't worry. It'll be okay. So, here we go. Now, these are just going to be sketches. Okay, so don't stress out. It'll be okay. I promise. When we do it, the reflection principle, basically we're taking the line y equals x, and we're reflecting over that line. So, if we had a function, that looks like this. So there's a point at -1, 0, there's a point at 1, 1, and there's a point at 1, 2 for sure. So that's what my function looks like. If you were to graph the equation y equals x, the new function is just reflected over that. What I like to do when I have to graph and find the inverse this way is I like to find, you notice how I labeled 3 key points? What I'm going to do is I'm going to find the inverse of them and replot them. So this point right here was -1, 0. So the inverse is going to be 0, -1. This point right here was 0, 1. So the inverse is going to be 1, 0. This point right here was 1, 2. So the inverse is going to be 2, 1. And then I have other things like right here where it touches. It's going to cross right there again. But now instead of going down, it's going to kind of go, I don't know. You got to think about folding the paper in half. You kind of make it look the same but tilted. It's not really a good way to, just kind of got to eyeball it.
So the line in the middle between ones?
That's what it got reflected over.
Yeah.
So like, oh, I love patty. So like here's a patty paper. Bellflower, yeah. So kind of think of it getting flipped over that line. I didn't do too bad. See how it kind of laughed? I lost a little, but not bad. Not bad. Anyway. Okay, I'll take C+. Is the function 1-to-1? So is the original function 1-to-1? Does it pass the vertical line test?
Yeah.
Did it pass the horizontal line test? So is it a function?
Yeah.
Is the inverse a function?
Yeah.
So is it 1 to 1? Yes. Some cool things happen with inverse relations. When you take the composition of them and their inverses, they will always equal just x. And that's how you can tell if two functions are inverses. But it has to work both ways. Inverse function of g if and only if this. So you have to be able to go both directions. So show algebraically that these are inverses. So the first thing I'm going to do is f of g of x. So I'm going to take my g function and plug it into my f function. Are you okay with the first step? So what happens with the cube root and the cube? They cancel, and so we're left with x minus 1 and then a plus 1, so that's just x. Nice. And then we have g of f of x. So then you got to go you got to do this one, this composition as well. So what happens with the ones? Cancel. And so you're left with the cube root of x cubed. So what are you left with? X. So if the directions, if somebody asks you to show algebraically the two things are inverses, that is what you do. You need to show that they both equal x. Both compositions. There's a peach-colored box on page 125 that gives you steps on how to find inverses algebraically. We're just going to try it, okay? So, here we go. Example 7. So, domain. What's the smallest thing I can put in there for x? Yep, so -3 and to infinity. And if -3 is the smallest I can put in there, what's the smallest y value I'm ever going to get out? 0. Bless you. So now let's work on the inverse. We're going to switch our x's and y's. So we're going to say x equals the square root of y plus 3. And solve for y. What do we do? Square it. And then what? But instead of y equals, I want us to use proper notation to show it's an inverse. Inverse of f equals x squared minus 3. And what would the domain be? What the range was? And what's the range? What the domain was. There it is. What do you think? Not too bad. So, and I gave you odds so you can check your answers.